Ben-Bassat. I'm a security researcher for Microsoft, Section 52.
And I'm Tamir Ariel, also from Microsoft, Section 52.
And today, we're here to talk with you about BadAlloc. BadAlloc is our code name for a pretty long list of vulnerabilities affecting memory allocators, mostly in real-time OSs and other libcs used in embedded devices. So just to make things clearer, what do I mean by vulnerabilities in memory allocators? Think about it like that. Let's say that you have a small IoT device with not a lot of RAM, and on that device, you call the malloc function, for example, which is one of the functions to allocate memory. And you ask it for a very, very large size of memory. So let's say 4 gigabytes. And then, what would you expect to get back? Null pointer, right? Because it would probably fail. But the thing is that in our research, we actually found out that in most cases, in most of those real-time OSs, it won't. It would actually return you a valid pointer to a valid buffer, but for a very, very small size, which leads us to security issues such as heap overflows, obviously. And in this talk, we're going to explain everything. We're going to talk about how it happens, why, where, what's the scope of the problem, and we'll see some examples. We'll start off with two quick reminders. One regarding integer overflows, which is super important to this topic. And the other one is about how memory allocators work in a high level, so don't worry about it. Afterwards, we're going to see some affected products to really understand the scale and the scope of this problem. And then we'll go and do a technical dive-in and see a working POC and explain everything and how these kind of vulnerabilities could be exploited to achieve remote code execution on those devices. We'll see a quick demo and end up with some mitigation techniques and a few minutes of Q&A.
OK. Hey, everyone. As Omri said, I will do a quick reminder about integer overflow. So let's start with a simple question. So 8 plus 8, everyone knows it. They can calculate it in the red. It's 88. Oh, sorry, not the right format. Let's check this out. Here, she fixed it. So 8 plus 8 is 16, but let's take a little more complex example. So 2 to the power of 32 minus 1. This is the very important number. This is the max int for 32 bits. Why it's important? Because if you will take this number and you will edit the number 8, the computer will think it's 7. Most important thing, it's on 32-bit systems. You would think it will be another big number, but no. The conclusion, it's a really small number. Again, with multiplication, 2 times 2, it's 4. But if you will take, again, the max int divided by 2 plus 1 times 2, it will be 2 and not another big number. And that's really important thing to remember in this presentation. So keep this in mind. Again, on 32-bit systems.
Thank you. So memory allocators. Essentially, on every device that we have any kind of memory or linear memory, we would want some kind of an allocator to manage it. So on that device, we would have 3 blocks and allocated blocks in red and green in this imaginary scenario. And essentially, it could be implemented in really, really high level in 2 ways, as either a single or a double linked list of 3 blocks. And once we're allocating a block, we're getting it out of the free list, and it becomes red in the slide and only holds a certain size property in most cases. And the thing is the thing that is important to this topic is just to understand that there is a certain calculation that happens. So when we're allocating a block, we're not allocating the exact amount of a memory area that was requested, but some extra space for the size property, for example, and might be other properties. So in that example, you can see that if we'll ask malloc for 1K bytes, it would need to do a certain calculation behind the scenes, adding the extra size of the header of the size property, and we will end up allocating, let's say, 1,032 bytes, 8 bytes more than was originally requested. Why is that important? Because if we're understanding the idea that the integer might wrap around on those mostly 32-bit systems, then there is a potential integer wrapping around in here when requesting really, really large sizes, almost integer maximum or near it. There is a chance that malloc, there is not a chance. Malloc would actually, the calculation would actually wrap around. The only question is either this malloc is safe, did it check for it, or it's a bad implementation, bad malloc, they didn't check for it, and now it would look at the number of bytes requested and would say, okay, 7, no problem, let's continue. The other example is with calloc, which is essentially a wrapper around malloc in most implementations again. And it works by multiplying the number of items requested and the size of each item. So in that example, we would ask 2 items, each one approximately half of the maximum size. And we would end up, again, trying to allocate 4 gigabytes, and would successfully allocate only 2 bytes, which is a pretty unexpected behavior that the developer afterwards that use calloc and use malloc is not aware of.
Okay, so we talked a little about integer-overflow. We talked about memory allocation. So we will do a little example. So we have the server. The server is safe. I wrote it. It's safe. I'm a good programmer. So we will look at this specific function. It's called read user data. It gets the user data and the size from the user. And the function, as you can see, will try to allocate the size to a buffer. If the allocation will succeed, the function will try to copy and then return the OK, thank you message. If it's not succeed, it will return sorry. And we have Alice. Alice is a good user. Alice wants to talk to the server. So Alice sends the hi message. Hi, 2 characters, size 2. So what will happen inside the server? It will try to allocate if it will succeed, because she asked only for 2 bytes. And then the memcopy will try to copy the user data to the buffer and return the OK, thank you message. Now, we also have Eve. Eve is a bad user. Eve will try to send a lot of a really big message to the server, and we'll check. She wants to check what happened. So the server will try to allocate it. It will fail and return the sorry too much data message to Eve. Eve is sad, right? Because the server is secure. And we have another example. We will change the allocation function to a bad malloc function. With Alice, everything will be the same. She will send the hey message. The server will return, OK, thank you. But Eve is the one that important to us. Eve will send the really big message. And the server will try to allocate this size that she sent. We can see inside the malloc function, we took a random malloc function from GitHub. It's from FreeRTOS, if you know the system. If not, Ben-Bassat will talk about it in a few minutes. And as you can see, there is some calculation there without even check the result, without even check anything. So the allocation will succeed. The memcopy will copy the data from Eve to the buffer, by the size from Eve, that we remember it was very big size, and will return, OK, thank you. That's not good scenario, because it causes heap overflow, and we don't want that.
OK, so we understand that once malloc is called, there is a certain calculation that might wrap around. In some certain scenarios, like in the fictional server that we saw, that might lead to an unexpected heap overflow, which is obviously a vulnerability. But at this point, you must be wondering, OK, how many affected devices there are that are actually affected by this kind of vulnerability that we explained to you about? So let's see a short list of operating system, real-time operating system devices and libcs that we actually found affected by this specific issue. And you might notice some big names in here, like VxWorks, which is probably the most popular real-time OS in OT industry, and is estimated to run on something like 2 billion devices. Then we got NXP's MQX, which is the second most popular real-time OS in the same industry, and it also runs on tons of devices. We have FreeRTOS, which is extremely popular with IoT devices. It's actually backed by Amazon, and it's the official real-time OS for their AWS services for IoT. There's Google Device SDK, the IoT Device SDK in here, sorry. There's MediaTek chips in here. There's ARM chips in here. There's Redis newlib, which is an extremely popular libc for embedded devices. There's micro COS in here, and there's Texas Instruments SDKs and devices in here, and some more, and that's really a partial list. And in every one of those, there is some function, some memory allocation function that was actually found vulnerable to this specific BadAlloc vulnerability. And it's not only the scope, like how many OSs are affected by this vulnerability, but what I also want you to understand that there is a specific nature to this kind of vulnerabilities where they affect the most basic, the most bare metal functions in those products. And those functions, malloc and calloc and similar allocation functions, in most cases were there for the earliest days of the project. And no one ever gets back and takes a look at the malloc and says, oh, wait a minute, I wrote this thing 20 years ago, and maybe I should check it for this new kind of vulnerabilities that I just learned about. No, it doesn't happen. And in the far end of the scale, you can see that VxWorks actually started from 85. MQX, early 90s, klibc, NATEX, FreeRTOS, all of these are from early 2000s. And no one ever got back and checked for issues in those functions up until this research and up until the disclosure that we did last year.
OK, so Ben-Bassat show you some of the most big names that we found. I will show you some examples that we think that are important to really understand what are you talking about. So we will start with VxWorks. This is from version 5.1 from 93. This is the earliest version that we could find online. And as you can see, in this line, we have some calculation that is trying to understand what is the size that the calloc function needs to allocate. And right after it, it uses it for the malloc function. So this is the calculation. Right after it uses it. What's the problem? It doesn't check the result. And as we said before, there is a scenario of integer-overflow. So there might be some attacker that can just allocate a really small size because he asked for a really big size, and everything will be fine. OK, So let's continue to klibc. Klibc is some kind of libc. It's a library from the Linux Foundation. It's used mainly in the early stage user space. And again, this line, this is the calloc function. This line is the problematic line. After it just uses the size that it calculates. But the interesting thing here, it's this date. This date is day or two after the project started. It's really important to understand that the author write a lot of function, a lot of code in a really short time, and he probably didn't check it right. But you remember one important thing, this line. Fix me. This you looked for a multiplication overflow. So he knew about the problem. He know that there is an integer overflow problem. It was in his head. But because he wrote a lot of lines, because he wrote a lot of code, he didn't ask for himself how he can preserve it, how can he prevent it.
Just forgot about it.
Just forgot about
19 years ago, he thought for a minute, oh wait, maybe I should fix it after lunch, and just forgot about it.
Just forgot. He remembered it when we asked about this function until 2020. So this problem was there for 18 years, give or take. That's what you need to remember about it.
Okay, so let's talk about some technicalities. We prepared a POC around this little chip in here. It's called SimpleLink. It's actually a line of chips from Texas Instruments. They're targeting the low-cost IoT devices market. It's a really nice chip. It comes with a pretty big software stack. So on the bottom layer, you can see that the developer can choose either to use TI's home-developed RTOS or FreeRTOS, which is, again, the most popular by far in this market. Then he gets the drivers layers and POSIX layer for compatibility and ease of use. Afterwards, we get the communication stacks. So Bluetooth, Zigbee, Wi-Fi, everything, every communication protocol is supported directly on the chip. And then we have the different plugins. So for example, cloud connectors to pretty much every vendor, AWS, Azure, Google's cloud, really everything, really nice chip and pretty low cost. And for the sake of this POC, we'll be focusing obviously on the POSIX layer, where actually all of the memory allocation functions are implemented. The wrappers are implemented for malloc and calloc. And we'll be running on top of FreeRTOS for compatibility. So that's how the SDK's code files looks like. On top, we get the heap-4, which is one of the memory allocator implementations offered by FreeRTOS, the one that TI's people actually chose for their system. And then we have at the bottom the memory.c file, which is where the memory allocation functions are implemented. And that's calloc from the same memory.c file. And if you notice, there's the n bytes calculation, there's some multiplication, but the real stuff is that line, which actually implements a good check, a check for integer overflow. So TI's people actually figured out that if they'll multiply pretty big numbers, it might overflow, so they need to check that they didn't get any null, so they want any zero, sorry, so they won't divide by it. And then there's the opposite function. They use division to verify the multiplication. So that's pretty good job from TI's side. But on the other end, that's malloc, same file, same memory.c file, only a few lines below. And if you notice, here is the vulnerability. That's BadAlloc, that's what we're talking about. Simple calculation, just one plus sign, but no check. The value that was calculated is just directly passed on to PV port malloc, which is the memory allocator from FreeRTOS. And that's not a good implementation. There's obviously a vulnerability in here. And if we'll ask for large enough size, the calculation would overflow, and then this malloc implementation would call the internal one with a very, very small size. So let's talk about exploitation. We understand that to trigger the vulnerability, we need to give it to pass on to malloc some very, very large size, and then we'll get some very, very small memory allocation. But we really wanted to demonstrate how this could be leveraged into a full-blown remote code execution. So in this scenario, we picked up the over-the-air update mechanism also built in TI's SDK. They give the developers, their clients, essentially, the capability to update those chips, to update the firmware of the internal chip and the firmware of the application remotely, directly from some CDN server that the client needs to have. And then it deploys on the chip. And everything is packed nicely with inside a single tar file with that file system structure. You can see there's like web pages in there, and there's the service pack, and there's the MCU flash image, which is the actual application firmware. But for the sake of this POC, the important stuff is here, ota.cmd. And that's how this file looks like. You can figure out from taking a look at it that it's a pretty simple file that holds the digital signatures for the other internal files so that they could verify the other internal files in the same update tar file. And why is that important to us? Because of the fact that this is the only file in the process that is actually required to be read fully into memory from the network. So you can see in this function that the file is actually read using some other getEntireFile function. So later on, they could verify the digital signatures of the other files taken from the ota.cmd file. So let's take a look at the internal getEntireFile function. It's not hard to figure out that it's a pretty simple function. There's essentially malloc in here. There's a check that malloc actually succeeded and returned the valid pointer. And then there is a memcopy. Up until this point, if I wouldn't know that malloc is vulnerable, there's no issue at all with that function. If we allocated enough memory, we can copy the buffer to that memory. It's simple. But this malloc, specifically from TI, is vulnerable. And the thing is that in the context of this POC, if you'll take a look, there's the file size in there. That property is taken directly off the tar file. So we, as the attacker in this scenario, have full control of the size that would be requested from malloc, and we can specify the integer maximum in such a way, or near, in such a way that would trigger the BadAlloc vulnerability in here, and would lead to a heap overflow afterwards, a control one with the memcopy. So how we can leverage this controlled heap overflow into a full remote code execution? Essentially, the idea is to find some kind of a function pointer that we can trigger a call to in memory, and then we'll mess with the heap from the FreeRTOS heap. We'll mess with it in such a way so the next allocation would be outside of the heap, would be in the area where that function pointer lays. We'll overwrite it to point to our shellcode, and then we would trigger a call to it. That's how the heap, specifically in FreeRTOS, looks like. If you know heap exploitation techniques from glibc, for example, they use the double linked list, but in FreeRTOS specifically, there's a single linked list, which is kind of a problem for us. But the idea in here is that we can create this redirection of the heap by overflowing and overriding the next free cell pointer in the next free block. So in this slide, we will override and change it to that address. So in the next allocation, the allocator would figure out OK, that's where I need to go. That's where the free block, the next free block is. So once we'll allocate something, it would be allocated on that memory area. And what is this function pointer that I'm talking about? So in TI's SDK, there's another component of a web server which could handle serving web pages in 2 ways. The first one would be static pages, and the other one would be a dynamic function handler. So it's pretty similar to CGI in a way. You just write a function in C that would handle some page. So for example, it could handle OTA.html, for example. So once I'll go to the web server and ask for OTA.html, it would go and search for the proper function pointer to handle it. And that's the function pointer that we want to override, because obviously we can trigger a call to it by asking a specific web page. That's how it looks like in memory. So we get the HTTP request array of structures in here. And the marked ones are the pointers. There's a bunch of them. And we just chose the specific one for the POC. So first, let's take a look at the exploit code. That's how it looks like. It's just a simple Python file. It's not even that big. And it starts off by creating the malformed tar update file. So in here, you can see that we're actually hooking the built-in tar library from Python. So we could mess with the internal file size of the internal files. So in this code, actually every file that we would create, we're creating only one, but every one of those files would be created with a fake file size of almost the maximum for 32 bits. Then we're going to upload this file, so the heap would be corrupted. And then we're going to create another request with the new pointer that would be allocated on the old pointer and the shellcode itself that we are using. And that request would be a simple HTTP request with everything in the user agent field, because the system actually allocates a specific buffer for the user agent. And that's the shellcode that would be compiled. Because everything goes on HTTP request, we need to have it null-free and space-free. So the shellcode is XORed encoded. Simple XOR cipher, just simple key. It doesn't mean to hide anything, just to avoid any nulls and spaces. So we got the XOR decoding stub in here that would execute on the device. And then we have our payload. So the idea in the POC is just to override the default index.html file. So it would refer the user to our own control domain. So we start off by stopping the SL dash are just TI's API. So we're stopping the network stack, starting it again, essentially restarting it to avoid any problems from the previous exploitation effort. And then we're just opening a file, the HTML index.html file in here. We're opening it with write permissions and overwriting it with our own HTML payload, which is pretty straightforward. It would would refer every user to our own controlled bed.com domain. And that's pretty much it. We're closing the file and rebooting the system. And that's the POC script itself. So let's take a look at the execution. Well, come on, Mac. Okay. Great technical effort. Okay, so in that side, you can see our fake POC system. It's just a web server that we modified on the device, on the device that you saw, the actual evaluation board with the SimpleLink chip. So that's the web server on the local network, and that's the script that we saw earlier, targeted to the device. So let's execute it. And let's take a look at what we're seeing in here. So first, there is the crafting of the OTA file with the hooked tar library. It was created so that the next chunk in the memory, in the heap, would be created at that address of the HTTP request structure that we talked about earlier with the function pointers. Afterwards, after it was created, we're going on to compiling the shellcode. So every time the script would compile the shellcode from scratch, so it's easily modified. You can see the actual shellcode in here. You might notice the strings in there. It's before the XOR encoding. And that's actually a marker, so we'll know where to start to encode from, to encrypt from. Then we're packing everything tightly into a user agent string and uploading the tar file, which messes with the heap. And that's the shellcode and everything after encryption and decoding and preparing the fake addresses and stuff. That's where the payload starts, and before that, we get the address and some other things that we had to have. So let's refresh our web page. And here you can see that we were referred directly to bad.com domain, which is, again, our own maliciously controlled domain. It says that that you have been hacked, but you don't need to worry about it. There's no money required or anything. And you probably can't see the writing in blue, but there is the blog post in there. Don't worry about it. It will be back in the link would be back in a second. Okay, so let's go back to the slides and talk about some mitigation techniques.
Great success.
Great success. Thank you.
Okay, so Ben-Bassat just showed you that he broke the device, but it's not finished here because we want to show you how you can fix your systems.
Or find some other
vulnerable systems. So the first thing is to understand your functions. This is just a small list of the most common name for the allocation function that we found. There are a lot other names. Every vendor uses his own. Maybe they do, maybe they just use the malloc, calloc, and realloc and this list. But you need to check the application that you need to understand what's the name of the functions in your applications. So how to start? Start by checking out the advisory that you will get the link in the next few slides. Second, just reverse engineer the binaries. It's always the best approach in life, not only in this scenario, always. We get a project, we reverse it. If you don't want to reverse and you have the source code, check it if it's public, if you have it.
For the weak ones.
For the weak ones. You can review the code. Most of the research that we done was from code from GitHub. So if you have the code, fantastic. And to do some kind of little unit test, try to allocate a big chunks of data, try to allocate a small size of data, see what happened, if there is a heap overflow, if not, if you got an error, if not. I don't know what you can get, but if it's good, it's good. And if you check the source code, it's also really recommend to check also the macros. If you reverse, you don't have the macros problem, but if you check the source code, check the macros. We found a lot of macros that had a problem with alignment mostly, and inside the macros, there was the integer-overflow problem. So this is a couple of libcs that we found that are good libcs that mitigate this technique in a good way. So glibc, I believe that most of you know it. Check the size, the bytes, and check if the size is logical correct. They just divide it after it to check if you get the n from previous. If you got it, great. If not, not so good. The next example is the embedded artistry. They do some kind of check. They decided that the malloc overflow is the biggest size that someone will need. Embedded artistry do libc for IoT mostly. So in the IoT, you have little RAM, so you probably won't need malloc of big sizes. They do another checks there. There's another good thing to do. And the last one is muscle, another calloc function. They check that the n size is not 0, and they check if it's logical correct again. If you can get, if it's in the right size.
Okay, so some final words. If you want to learn more about it, please go out and check out the advisory on ICS-CERT's website, CISA's website. All of the technical details are in there. There's the full list of affected devices or affected products, There's approximately 30 affected products in there, so that's a lot. And almost twice as much as CVEs for each of the functions. You can find it in this QR code. You can also go and check out our blog post in MSRC's blog. Just search for the ID in your favorite search engine.
You can check the QR code. It's not a virus, we swear.
And also, I want to thank CISA and MSRC, which did amazing job with the disclosure. So 30 vendors is not easy, and they really put the effort on it. And for months, they went after each and every one of the vendors and made sure that everyone is aware and that they know about it and that they will fix it. And really amazing job, lots of work, and I really want to thank them. And I also want to thank you for listening, and I hope that you enjoyed it and you find it useful. And that's it. So thank you. And now we have a very, very short window for Q&A, but we'll be in the wrap room on the other side of the hall. So please, if you have any questions, you're more than welcome to come visit and ask them. Thank you. Thank you.